welcome everyone thank you for attending this webinar done by Telops, with Exosense being our parent company. We'll be joined today by Marco, who's from MIT. I'll introduce him briefly later on. Very exciting work that he'll be showing us. So I'll give a little bit of time for other people that might be joining us. I see more and more people are coming in. So I'll slowly start while this is in progress. So today we'll be talking about a really fascinating application of IR imaging. So we'll look at the hidden power of boiling, heat transfer and boiling in fluids using IR imaging. So my name is Antoine Dumont. I'm a field application scientist at Telops, and I'll be joined by Marco that we see down here, Marco Graffiedi, who is at MIT in the Red Lab working on this application. He's under the supervision of Professor Matteo Bucci. So today we'll go over just a quick overview of Telops, and I'll present our product line with a few examples of fluid dynamics or fluid imaging with IR cameras before I hand the presentation over to Marco. We'll finish, of course, with questions and answer. So in the GoToWebinar page, there's a little question tab here. So just at the bottom of that window, so you can put in any questions that you have during the presentation, and we'll go over those at the end. So before we really get started, we always like to share a little poll with our audience, just to understand a little bit more your experience with IR imaging. So you should see this popping up on your screen now, and just click on the screen towards the answer that represents your experience with IR imaging, how you would rate your overall knowledge of infrared imaging technology. I'll just give it a few seconds to see what kind of audience we have with us. There's no wrong answer or bad kind of audience. We love everyone attending a webinar, from no experience to thermal imaging experts. We always have some really interesting questions. All right, maybe another 5 seconds. And I'll close the poll. Oh, image sort of shifted. Okay, so we have the results of our poll. That's really great. We have quite a few people that do have direct experience with IR imaging. So hopefully you'll have some interesting questions or insights or comments for this presentation. Other people no direct experience and are either interested or have considered the technology before. So great, thank you for coming in, and feel free to put in any questions, write in any questions you have during that presentation, like I said before. So we'll do a quick overview of Telops. So we're talking about Telops cameras. Telops is an infrared imaging manufacturer, let's say infrared cameras manufacturer, yes. We are based in Quebec City. We're founded in 2000, so we just celebrated our 25th anniversary. We now employ about 100 people, quite a few people with advanced degrees, PhDs, masters, engineers of all sorts. We really have a large section of R&D, so really try to push the technology, being at the cutting edge every year. So we're really proud of that. We've established ourselves as thermal imaging leaders, offering solutions of all sorts throughout the years. In 2023, we joined Exosense as part of a large group trying to cover the whole electromagnetic spectrum. So that's a really exciting adventure that we're starting with that group. We're hoping that it brings more collaboration and solutions to people. We have a whole suite of scientific infrared cameras. We'll talk about more about a specific branch today, but we offer from aerial methane leak detection to other hyperspectral system, fast cameras, entry-level cameras. So exciting tools for anyone dealing with applications in infrared. So we can see our whole suite of cameras that we have here. So at Telops, we started more with hyperspectral cameras towards the beginning. We are really proud to have some of the most advanced technology out there. We have hyperspectral camera in the midwave and longwave infrared bands. So this is the Mini XLW. We have airborne systems, ground system units, really powerful tools to have a high spectral and spatial resolution. We have an in-between broadband cameras and hyperspectral cameras. These multi-spectral cameras allow to have a broadband cameras behind 8 filters that rotate to have a continuous acquisition with 8 different spectral bands. So that allows you to go faster during the acquisition while having still a certain level of spectral resolution. And then we land in the broadband cameras where we have a unique band during the acquisition. You can still rotate some filters inside the camera, but during the acquisition, you have a single window or filter for your detector. We have high dynamic range cameras, a brand new technology that's quite amazing, changing really the paradigm of IR imaging with that new HDR camera that came out recently. Fastest IR cameras in the world are IR cameras going up to 100,000 frames per second. Then we have the entry-level cameras, so the Radia cameras, midwave or long-wave cameras, much cheaper, but still those new cameras offer the same scientific data quality that the Telops cameras have been offering over the years. So a quick glance at the multitude of applications that do use infrared imaging. We won't talk about all of these, of course, today. But just a few examples, we have ballistics, combustion, IR signature as a general application, gas detection, cold spray, experimental mechanics, additive manufacturing, which is quite a growing field, NDT, non-destructive testing, which can fit from solid to fluid imaging as well, mineral identification, and then fire research. I didn't even put fluid dynamics here. We'll be talking about that a bit more for the rest of the presentation. So quite a lot of work out there using infrared imaging for a multitude of applications. So I want to go over some of the camera specifications that will typically be used in fluid dynamics. It's quite a changing field in terms of what is needed, what kind of camera you would need for this application. You could say it's fluid in a way. Sorry about the bad pun. But in this field, the midwave series, when we talk about midwave camera from 3 to 5 microns or the extended range from 1.5 to 5.4, it's a good, reliable range, have a good image for the thermal aspect of your scene. And it's also the range of cameras that have very solid detectors with reliable high speed compared to the other bands. So if you do have high speed phenomena happening within your fluid or on the surface of your fluid, that's where you need those models that push the frame rate for your acquisition. So M3K is the fastest model. We have the M2K. M2K UD is an interesting new model that's in between, offering a slightly higher spatial resolution, like we can see in the window, detector format size. But it also allows that high speed acquisition. So that is a good in between for spatial and temporal resolution. Otherwise, if you really want to push that spatial resolution as much as possible, if you don't have a particularly high speed phenomenon, then you can go into the HD range, which are really large detector that offer a resolution as high as 1920 by 1536 pixels for one image. So nice, crisp, and high spatial resolution image that gives a lot of information for your image. It's important to remember that with the image that you get for these cameras, every single pixel has a radiometrically calibrated data point in it. So every pixel has a specific temperature point or radiance or irradiance, depending on what kind of data you want to use. I wanted to mention those new cameras, the M100 and V60 radio cameras. They're much smaller than those bigger cameras, those high-speed cameras. The Radia V60 at the top fit in the palm of your hand. Very small, very easy to integrate within any system. So the V60 is long wave, great for any sort of low temperature heat transfer measurement, body temperature, low temperature fluids. You have a very nice high quality image. You have that spatial resolution of 640 by 512, which is quite nice. Same resolution for the M100, but in the mid-wave range. So typically more for high temperature systems or processes. That will be a great tool to use as well. So it's an entry-level system. So typically more aimed towards people that are not like experts in the field of thermal imaging or infrared imaging, but they have the same unique calibration method that we use at Telops. So they offer a really high level of data quality, regardless of the fact that they're entry level. You have that low swap packaging, user swappable lenses like the other cameras, and that nice permanent radiometric calibration that we offer from Telops. So they don't need to be recalibrated in the lab. Now we're talking about measurements in fluids on fluid surfaces today. I'd like to talk about the requirements that we typically see for these fields. Of course, we want a good spatial resolution. We want that spatial information as much as possible for what's allowed within your process. So a mid-range spatial resolution, 640 by 512, can offer the good in-between of balancing speed and spatial resolution. Within fluids, you need the ability to detect small temperature, small defects that are created within fluids, nucleation of bubbles, like Marco will talk about a bit later on. And if you're trying to do measurements within fluids, sometimes it's good to try to optimize the spectral band for your measurements. You need to understand the emissivity properties of your given fluid, because that changes quite a bit from one material to the other, from one fluid to the other, and from what state of matter to the other. We can see that water vapor doesn't have the same IR response compared to liquid water and ice as well. They have different absorbance or transmittance depending on their state. So that's critical when trying to do that infrared analysis, especially if you're trying to do surface analysis for heat transfer or vortices analysis, or if you're trying to do even internal measurement, which gets even trickier, where you really have to take into consideration the transmittance of your system. Like I said, the acquisition speed varies quite a bit depending on the phenomenon you're studying, and the small bubbles that might be created, any defects, any small vortices created, sometimes can require microscopy imaging, which is certainly possible from far away or closer inspection. But microscopy obviously causes a much narrower depth of field, which can be challenging during your measurement. So it's quite a varying application. So there's no unique recommended models, I would say, for this type of measurement. If you're doing a measurement on fast phenomena, the M2K-UD that I mentioned earlier, having a good bit of balance between spatial and temporal resolution is quite a great model. If you're pushing the speed, M3K is the thing for you. Or if you're looking more at heat transfer at lower temperature, then the V1K in the long wave is interesting. For slower phenomena, then you have the L200 grid image in the long wave as well for heat transfer. Same for the V60, a much cheaper entry-level option, which with a grid image, or the M350 in the mid-wave band. So I'll go over just a few examples. So here I'll look at some water surface temperature measurements. This was a project where we were using a mid-wave camera, so the M1K with a 640 by 512 pixel window. And for this particular project, they were requesting a custom cold filter at 3.9 to 4.2 microns. Why a cold filter like that? And then that can isolate your measurement. So take away any kind of emission that you have from gases in the atmosphere between your scene, so your fluid and your camera. So in this case, we're trying to take away any noise, any signal from gases between the scene and your camera. So having that through flame region that we have here, where you don't have emissions from other gases. And then you have that pure temperature measurement that you have from your water skin layer that we have here. So an interesting test, so those were just the test measurements that were taken at Telops. A clear view of those vortices, of the difference in temperature on the surface of the water, regardless, even if it's a very small temperature difference, our cameras are able to differentiate those temperature gradients quite well. If we're trying to push that spatial resolution, we have the equivalent measurement here, but in a warm water tank with a Super HD system, sorry. So that was the M3 Super HD model, where we had a very clear imaging of those thermal boundary layers in the water. And with the disturbance of the water surface, we can see those those warmer water regions just breaking the surface, coming back towards the top with those vortices appearing. And if we're doing more of a dynamic analysis of fluid droplets like we have here, so that was done with a lens, that was done as well with a microscopy lens, like the image that we have here. So this was an analysis of the impact of the surface roughness on the mechanical and thermomechanical behavior of those droplets. So we can see quite a different shape depending on the type of surface those fluid droplets would land on. And they were analyzing where the heat transfer was happening depending on the impact that we have here. So these kind of tests are very difficult, needs a lot of optimization depending on the depth of field you have with your lens here. It's quite narrow. Camera at an angle, those very short single event scenes. So a nice measurement that was done at that University of Sherbrooke with the group in mechanical engineering. I'm done talking about my quick examples. I want to leave plenty of time for Marco to talk about his work. So their work at MIT, that was really interesting. So Marco Graffiedi is a PhD candidate in the nuclear science and engineering at MIT and is part of the Red Lab. So he researches the boiling heat transfer in cryogenic and dielectric fluids for applications in space exploration and electronic cooling. Prior to his doctoral studies, Marco accumulated 4 years in experience in the oil and gas industry, working at Baker Hughes in roles ranging from test engineering to measurement systems and participating in the company's prestigious Edison Engineering Development Program. The Red Lab at MIT, that is led by Professor Matteo Bucci in the Department of Nuclear Science and Engineering, pioneers innovating research and heat transfer to enhance the efficiency and safety of energy conversion systems, with a primary focus on boiling heat transfer for nuclear energy applications. The lab develops advanced diagnostic tools and leverages micro and nanofabrication techniques to engineer heat transfer surfaces, enabling unprecedented insight into the mechanism of boiling and two-phase flow phenomena. So Marco, I'll let you take over the presentation. Let me just give you the power to do this. Here you are as the full presenter.
Oh, okay. Thank you. Thank you very much, Anthony. So I'm not sure if you guys are able to see my screen, so just asking for confirmation. Yes?
Yes,
okay.
It worked well, yeah.
Perfect. Okay. Okay. So as introduced, yes, I'm fourth year PhD student at MIT, and so today we're going to talk about a couple of experiments. One is like mine that I'm doing in collaboration with the University of Pisa, and the second one is actually from a colleague of mine, Gustavo Anguyar, who actually defended his PhD 2 years ago. Just to give you an idea of about what boiling means, at least in our team, it means two-phase heat transfer, which spans across multiple industries and multiple applications. So, for example, we can see that 80% of the global energy production is actually from boiling, so like production of vapor, which actually gets into our Rankine cycle to actually produce energy. Boiling is also used for electronic cooling. This is actually an emerging technology in the sense that right now there are some companies, startups that are starting to actually commercialize fluids and system to basically cool the electronics by full immersion. And also, well, of course, in the chemical industry and in the cryogens, let's say, workspace, which also means rocket fuels. So that's actually another part of my research. I focus on electronic cooling and cryogenics. So let's start from the basics because I don't know exactly what are your backgrounds. So the boiling curve can be sketched very simply. So you have at first at low wall superheat and low heat transfer. You have basically a linear behavior, or well, sort of, which is in single phase. So you don't have any bubbles yet, right? And then there is a moment where you reach a certain wall superheat and you start having bubbles. So this is called the onset of nucleate boiling. And after that, you start having bubbles on the surface, right? And then if you increase the heat flux or the temperature of the wall, you can find more and more bubble crowding the surface. Now, at some point, you're going to have a regime which actually becomes unstable because you start having too much vapor on the surface, which means that you can reach a critical point, which is very important in boiling heat transfer applications, because this is basically the end of a very nice range of heat transfer for your fluid or for your specific application, where you have a very high heat transfer rate with low wall superheat. But what happens when you get to the critical heat flux, you go to film boiling, which is also called Leidenfrost effect. In that case, you can have a runaway of the temperature, especially if you are controlling the heat flux. Because the heat transfer capabilities of your fluid drops because you have vapor. You have a thin vapor layer between the liquid and your surface, which actually acts as an insulator. And so, as you can see from this very nice video from Adidian, you see that the surface actually becomes bright red. So it's actually emitting in the visible light, in the visible spectrum, because it's 1000 degrees C or nearby. So let's move to the experiment that we developed here at MIT in collaboration with the University of Pisa. This is an experiment on dielectric fluids. So we are using, in particular, FC72, which is a non-conductive fluid that can be used in electronic applications. And here we are studying actually the effect of the electric field on the boiling process. To do so, we have this test chamber that you can see here. Inside of this test chamber, you have a heater, which is assembled between two grids. Well, one grid and a foil, which basically is the ground. And then the heater, which is the most important part of our experiment, is made by a sapphire slab, a very thin slab of sapphire with ITO and silver pads coated on it. The ITO film is opaque to the infrared light. So as Anthony showed you, right, the spectrum of water for, let's say, the emission of IR, it's peculiar to water, and then you have a peculiar spectrum for vapor, and you have a peculiar spectrum for FC72 as well. But in this particular case, what we are doing is we are putting between us well, between the camera and the fluid, a film which is opaque to IR. So what we are actually measuring from the thermal camera here, which is looking at the bottom of our sapphire, is the temperature of this ITO film. So we're actually measuring the wall temperature between the solid and the liquid, which is very interesting because you can use it, as we will see, to infer other properties of this boiling heat transfer. In passing, just to clarify, sapphire is actually transparent to IR, at least in the range that we are working in. So it's between 2 and 5 microns of wavelength. And yeah, so this is the experiment. Let's go and see what are the detection mechanisms that we have. I'll start from the phase detection, just because I think it is the clearest way to see the boiling process. This one is done by using a normal high-speed camera. When I say normal, it means in the visible spectrum. And we use a coherent LED light that is shining at an angle to the surface, to the ITO film. This light is actually reflected back and captured by the high-speed camera. This reflection that happens here actually depends on the on what phase, vapor or liquid, is in contact with the surface. If the liquid is in contact, the liquid has a higher index of refraction respect to vapor, and it's similar to the sapphire one, so more light is going to come through, and so it will appear dark in our image. So in our image, when we see dark, it means liquid. While if we see bright, for the same reason, we are seeing that vapor is in contact with the surface, because vapor has a lower index of refraction, and so we have a higher reflection of light. So this video, which is recorded at 30,000 frames per second, shows you the population of bubbles on the surface with a very high resolution. And our objective here is actually to take this information, so we know where the bubbles are in the surface, and combine it with the IR camera. Now, just to show you, before going into the IR camera, I want to show you how, let's say, these video look like in the different regimes. So in the onset of nuclear boiling, you have some bubbles on the surface, but it's not very much crowded. Then you have nuclear boiling, and then you are very near to CHF. Everything seems to be covered by vapor, right? Now, if we look at the IR, actually, what we see is that we were using fast 3K Telops camera with a 260 millimeter lens, so basically a microscopic lens. And we were imaging only a part of our heater, just because we weren't able to image the whole heater with this resolution. So, and this is because we wanted to actually record a 3K, so a 3,000 frames per second. So here you see the image of the IR camera, which is superimposed to the phase detection camera. We have some marks on the side to basically align the two. And then what we can do is we can take the results from this IR camera, we can post-process them. So we find the temperature, which is, I mean, it depends, that is easy, you just need to use the calibration. And then there is an inverse problem that you can solve, and we will see how, to find the heat flux between the wall and the liquid locally. And here you can see the combination between the phase detection and this heat flux between the wall and the liquid. But we will see this a little bit better in the future slides. So here it is, right? So here we have basically the measurement of the temperature. You see it on the top. And from the measurement of the temperature, you can kind of see that something is happening, but it's not really clear because the temperature difference between vapor patches and liquid, it's not stark for FC72, while it's much starker for vapor, for liquid water and water vapor, and we'll see that in the experiment of Gustavo. But in this experiment, we had this kind of difficulty to solve. So we tried to use the inverse conduction. You see that at first it's kind of, let's say, all initialized, because this is actually the solution of the differential equation. So we are solving basically the conduction in the substrate using the temperature as a boundary. And this gives us the heat flux on the surface. Now, if we combine this with the phase detection, we can actually start seeing that bubble, at least larger bubbles, they seem to be characterized by a lower heat flux, almost zero, right? Which is what we expect. So here I'm going to show you a higher heat flux. Yes, so if we move from a lower heat flux to a higher heat flux, you start seeing a little bit better that bigger bubbles are characterized by a lower heat transfer rate. And then if we go even higher, it should be even more clear that largest patches have basically almost zero heat flux. Now, unfortunately, the results are a little bit noisy, and this is because we are looking at a variation of temperature on the surface of 0.2 degrees, which we are recording at 3,000 frames per second. So, yes, clearly from the image that I showed you before, we can kind of infer that we are measuring the right thing, but for FC72, this process is not as clear as you'll see in water. So we decided not to publish it for now, and we are working on it to make it better. But I wanted to show you because we are like very close to get this working. And here you see basically the temperature measurement history in time, and then you have the heat flux history in time, and you have wet and dry area of 1 pixel. And so here basically you can see that when it's dry, for some reason, this pixel in particular, when it's dry, the heat flux actually goes up, which means that we are looking at a lot of noise in this measurement. So I'm going to move to Gustavo's experiment. This is done in water, and what he did is to do a very similar analysis, but in this case it's for water on rough and smooth surfaces to see the differences between the heat transfer mechanism at the surface. And here you can see, here you're already seeing the result of the inverse conduction problem that I was talking about before. So you can see the heat flux around the bubbles, right? So the bubbles are blue because basically he removed the footprint of the bubble, which actually has a very low heat flux. And we see that around the nucleating bubble, you have a spike in heat flux, right? And then you have a spike also when the bubbles are leaving the surface. So we are actually using this to probe the microscopic mechanism that characterize the boiling process. And so you can, and using this, you can do a lot of analysis, and you can kind of like understand if the heat transfer is happening, for example, when the bubble is nucleating, or when the bubble is leaving and the liquid is rewetting the surface, right? Or if you have, for example, microlayer formation, which was not the case here. Then I'm moving on to another experiment of this, where basically he was measuring the heat flux in annular flow and flow boiling. And here you can see basically that the heat flux depends on the amount of liquid that there is in the test section. So for example, if we have a liquid film, then a thick liquid film, then we have a departure from nucleate boiling, and you can see basically the spike of the heat flux that starts from the top. So basically it's like the crowdness of bubbles, right? Well, if you are in very thin film, then you have film dry out. And so in this case, you have this dry out of the film, and you can observe that the heat transfer where there is a vapor film actually disappears. So like you have a very low heat transfer. So in summary, we saw that basically the IR measurement in boiling and transfer can be used to measure the temperature field on the surface. By using the temperature field of the surface, we can infer the heat flux, right? And we can combine this heat flux with the phase detection in order to develop some what we call heat partitioning models, which are those, let's say, microscopic mechanism that characterize the boiling process that I was mentioning before. And we can show also the effect of different surfaces on local heat flux and heat flux mechanism. And we can use it ultimately to understand the CHF, so the critical heat flux, and basically the boiling crisis, which is basically the critical point of the boiling process, and which basically limits our working space, our engineering space for boiling heat transfer. So this is what I had for you today.
Great. Thank you very much, Marco. That was really interesting. So I'll invite people to write in their questions. So we already have some questions that were submitted. So first of all, there's just a quick question about mirrors. So concerning the mirrors, what kind of mirrors are those? So what kind of coating? What kind of coating do you need? That's always an important question. So I'm curious to know, in your setup, what kind of mirror you did use.
So we typically use a silver mirror, unprotected, when possible. Otherwise, for example, so in my experiment here, I don't know if the mirror was visible. We had a very big silver mirror, but now I'm actually using a hot mirror, which is fine for the let's see the mirror is here. It's not super visible, but now I'm using a hot mirror because basically sometimes you need optical access from here to use a different technique, which is called backlit shadography. So basically you shine a light from the top and you need to basically collect it with another cameras. So yeah, so we typically use hot mirrors, which are typically ITO coated, or we use silver mirrors.
Okay. Great. Another question about Gustavo's work. Is there also an ITO film for Gustavo's work? Wondering how this can be applied to a thin metal sheet. Will the heat inertia of the material be enough to dump any reliable measure? I had a similar question. Yeah.
Yes. So okay. So okay. Gustavo's work actually, when you see like these smooth and bare surfaces, this is actually it should be chromium coated on the sapphire. So it's not really ITO, but it uses both. So it uses both chromium and ITO. So when you say dumping, I am not sure exactly what you mean by dumping. So I know there are some experiments which are made using very thin foils of metal, right? And of course, you can use IR cameras in that case too. In that case, it's a little different because what you're measuring is the temperature at the back of your foil, which is very thin, and so basically you can consider it to be, isothermal. In our case, we have the sapphire, which of course has like a certain thermal inertia and everything, and then we have this very thin ITO coating on top, which we use to measure the temperature. So by doing that, we can do the inverse conduction problem, right, and find the heat flux, because we know that we have a 1 millimeter sapphire below and we have this temperature map on top. If you're measuring on a thin film of metal, for example, then you're gonna need to use the temperature at the bottom, right, as boundary condition of your problem. I'm not sure if that works. I have never tried.
Okay. As a sort of a follow-up to that, I had a similar question, but if you go back to whichever slides you have a video of that heat transfer. So I think the one just before potentially, or like these ones, it's a good example. So you talked about doing measurements at 300 hertz.
Yes.
Between each frame, are we talking about 1/300th of a second, so below a millisecond between each frame in this case?
So this in particular, which is Gustavo's work, I am not exactly sure. I could dig it in case if you want. We can look at let's say for a follow-up eventually. But for this one, so we are recording actually at 3,000 frames per second. So our integration time, I think, is around 100 microsecond.
Right.
Yeah. So the counts are in the right range. So we are like about let's say between 16,000 and 20,000, 24,000. That's basically our count range, which should be like in the sensitivity of the instrument.
And so with that, the motion of the fluid against the surface, how many frames approximately do you have? Let's say we're filling one bubble forming there. What's the speed of that movement for the bubble?
So this is a very good question. The answer is it depends. It depends a lot on the regime. For the phase detection, we are actually running it at 30,000 frames per second. So we do have a much better temporal resolution. For the IR camera, the problem is that you need to decide. So you have a lot of parameters to work with, right? So you need to basically decide if you want to run at 3,000 frames per second, or if you want to run at higher speed, higher frame rate. But if you use a higher frame rate, then your integration time is going to go down. So your sensitivity is going to go down. And in this case, we're looking at a very low temperature variation on the surface. About the speed, the bubble are quite, let's say, we're talking about centimeter per second. It's very normal, let's say, for any process, any boiling process, nothing particularly weird. But the difference maybe between this and water is that bubble tends to be much smaller. So having much smaller bubbles means that you have like a bazillion bubble on the surface, right? And so your IR resolution needs to be very high. So in the lab, I'm actually I think the only one that is using the 260 millimeter lens because for this experiment we do need this high resolution to actually capture what happens while the bubbles are growing.
Right. Okay. All right. Thank you. Another question that came in, I think maybe after that we might wrap it up. So thank you for the great presentation and for your time. Question, using a different fluid with very low IR absorbance in addition to a zinc selenide window can allow direct measurement of the solid surface in contact with the fluid. So basically from the other side of what you have done. Do you think that would be possible and is it feasible? Might eliminate some noise.
Okay, wait. You have to I think you have to reread this again because so it was a low absorption IR fluid, right?
Yes, in addition to a zinc selenide window.
Zinc selenide, which is very good at transmitting IR, if I remember well. I don't use the okay, perfect. So okay, so low IR fluid, low zinc selenide, a low IR, let's say, substrate, and then basically using the ITO.
And then, well, the question was, I don't know if the person that asked the question can clarify maybe, but asking about doing the measurement of the solid surface in contact with the fluid.
So
on the other side, so they say on the other side of the fluid, from what I understand.
On the other side of the fluid. Oh, I see. Okay. So basically, you have okay. So you have the same situation, but you don't have like an ITO film, and the liquid is basically transparent to the IR. And so now you're trying to see something that is on the opposite side. I have never tried. So especially if we have heat transfer, I bet that we're gonna have a lot of like image deformation, I guess, because of the fact that like if you have temperature, so if the liquid has different temperature, it has a different index of refraction, and so you have aberration of the image, right?
That makes sense. Yeah.
But in this case, like, well, it depends on the application, but I feel it might be very, very difficult to do that kind of measurement. I don't, Anthony, what do you think? You are also like, you're probably more expert than me in this.
Less of an expert for fluid measurements like that, but I think you're bringing up a good point with, if I understand the question correctly, imaging through the fluid, you would get quite a bit of distortion. There's the movement, the difference of temperature, so it would be difficult to image the surface on the other side.
Yes, and this is true in single phase. Like if we start having two phase, I think it would be like horrible to measure, right? But maybe no, maybe it's like everything is super transparent to IR, and the index of refraction is always the same, and you see through the bubbles, and maybe.
Yeah, you would have to know that the index of refraction, how much it's impacted by the temperature and the.
Yeah, but
in the
I
fluid,
wouldn't bet on it.
So I don't know if that was a satisfying answer to the question. Let us know if it was. If you do have more questions, please contact us.